The second meeting. And
Oh my God.
we started the way
Yeah, we had to argue that. I was like to make. I got 5 involved. I am, because you have.
I'm not, I'm not, like, we're this already like, Vegas, I'm just gonna ask her. Oh, wait. I know you don't. I have practice.
Yeah.
It's not practice.
I got to.
Oh, yeah. Okay, you also have the.
Everything else I thought.
Like, actually, so.
He made it for me.
Okay, so today we're going to start Unit 6. So we're done with derivatives. We're moving on to antiderivatives, integrals. So we know that derivatives is related to slope. And slope is rise over run. Yes. And rise over run is basically change in y divided by the change in x, right? That's slope. But antiderivatives is basically we're working backwards. We're undoing this process. And if we undo the process here, if we do the opposite operation of division, what's the opposite division? Opposite multiplication. So if I do change in x is going to be some change in x value. But if I multiply these together, change in x times change in y, that's basically the area formula of a rectangle, right? Length times width. And so that's why when we talk about antiderivatives, a lot of times we're going to be able to involve area. It's just going to be a natural, it's going to be a natural thing that we can find. So derivatives is all about slope, and antiderivatives, we're undoing the process, true, but it can help us solve for area problems because we're undoing this process. So a lot of things that we talk about with antiderivatives involves area or area under the graph because we're undoing that process for derivatives. Okay, so today and tomorrow, we're mainly going to be revolving around approximation with area. And then we're going to find the exact area using limit definition, and then we'll have a much more efficient process with power rule that we learned, that same process as with derivatives. Okay, so we're going to be focused on area between the graph and the x-axis. So the area under the curve, when we talk about area under the curve, under doesn't necessarily mean below, it means between the x-axis and the function. So x-axis, very clear. So this is my x-axis here. Here's my x, here's my y. If we're talking about the graph under the curve, it's between the curve and the x-axis. So we're talking about this shaded region here, if it's for this graph. If it's for this graph, then we're talking about this shaded region here. And then if we're talking about this graph, then it'll be this shaded region. Okay, so it's just between the graph and the x-axis. So let's take a rate of change function and examine its graph. The area under the curve gives us the accumulation of change. So let's say you're on a road trip and you have the car on cruise control for 4 hours. You travel 60 miles per hour. How far have you traveled? Well, if you travel 60 miles per hour over a 4-hour period, the hour units will cancel out and you're left with 240 miles. Right. We can also think of it this way where, okay, if I have my velocity function and my velocity function gives me how fast I'm going at a constant velocity. So my constant velocity over a 4-hour period, it's just going to be 4 times 60. So if we're looking at the velocity function, if we take the area between for the velocity function in the graph, we're going to get up to our position or our displacements or our distance. Right? So if we want to undo, if we want to take the antiderivative, let's say we want to go from velocity back up to function, we're going to be involving area. Okay? If we want to get from position to velocity, we're doing slope. And so we see that undoing process here. If we undo our derivative, we're using area to get up to that original function. So the units for area under the curve, the dependent unit is multiplied by the independent unit. So in other words, it's going to be a unit for y times the unit for x. So whenever we do an antiderivative, every time we find the area, our units will not stay the same. It's going to have to change. So the graph below represents the rate at which water is leaking out of the tank. The units are given in the graph. So we have gallons per minute. This is the rate at which water is leaking out. So it was 2 gallons per minute, and then it rises up to 4 gallons per minute, and then it goes down to 2 gallons a minute, and eventually it's going to stop. Okay. So how much water has leaked out of the tank after 9 minutes? So we know that we're looking for the amount of water, so our units will have to change. And what's happening is that we're multiplying gallons per minute times minutes. So whenever we're trying to find an area, we're always going to multiply units. And just like here, right? If you find area, you're going to be multiplying units. If you multiply a rate by a time, you're going to end up with the amount in gallons. So we're just going to be involving area. So if I find the area between the graph and the x-axis, that's going to allow us to find the accumulation of this rates over that time period. And if we have a bunch of gallons per minute data, then eventually our accumulation is going to give us the total amount of water in terms of gallons. So the area that we see here is going to indicate how much water is going to leak out of the tank after 9 minutes, because we have all the rates available to us. Now, these are all nice geometric shapes. So we can just find the area of all these shapes and add them together, and that'll give us the amount of water that's come out. So I see, let's see, I see a rectangle here. That's an easy shape for me to find the area for. So that's going to be 6 times 2, which is 12. I see a semicircle here. Semicircle, my area is 1/2 pi r squared. What's the radius of the semicircle? 2. So 1/2 pi 2 squared. 4 over 2 is 2, so 2 pi is my semicircle. And then finally, you have a triangle, which is 1/2 base times height. Sorry, it's 3. 1/2 base times height. So 1/2 3 times 2 gives me 3. So then if I add all those up, that will give me the total amount of water that's leaked out. Our units have to change, right? We can't say, oh, this means 15 plus 2 pi gallons per minute, right? So whenever we're involving area or antiderivative, our units will always change. And if we're involving area, we're always multiplying our units together. So if we add these up, we get 12 plus 2 pi plus 3. So in total, we have 15 plus 2 pi gallons. Notice our units have to change, right? Gallons per minute times minute is going to give us gallons. Okay, so today is all about involving finding area of a region. And right now, the area is all going to be nice geometric shapes. And we just have to keep in mind that every time we involve area, our units have to change. And because area is always width times height, or 2 units multiplied together, we always have to multiply the independent variables unit by the dependent variables unit, and that's going to be the new unit. Okay, so remember, anytime area is involved, we can never change. We can never keep the same unit. The unit always changes. Okay, so we have all these instances of problems where we're involving area. So particle is moving along the x-axis, multiplied by r of t. How far, and r of t represents speed because it's centimeters per second. So this particle is moving along the x-axis. And if it's above the x-axis, that means it's moving to the right. This below the x-axis, that means it's moving to the left. And then above, he's moving to the right. So that means he's stopping at 2, he's stopping at 8, and on either side, he's either moving to the right or moving to the left. All right, so let me shade in all the regions that we are concerned about. And these are all nice geometric shapes. We just have to find all these areas of these regions. Okay. And because we're talking about displacements, we have to keep in mind that these are all positive units, and these are all going to be negative units. So this will indicate him moving to the right. The accumulation of the area will indicate to him moving left, and then we can find all these areas. So I'll just do the math for us here. So triangle here, 1/2 base times height, 1/2 2 times 10. That's going to give us 10. I see a triangle here. In that triangle, 1/2 base times height, negative 22.5, because the area is 22.5, but this indicates he's moving left. An accumulation of centimeters per second is going to give us centimeters. So it's going to travel left 22.5 units. There's a rectangle here, 1/2 base times height. That's negative 30. Or 30 is the area, but then negative 30 indicates displacement. There's another triangle there, 1/2 base times height. Then 1/2 base times height here is 10. So that means the area indicates how far he travels. The line indicates what speed he's moving at, but the area indicates how far he's traveled. So he's going to travel 10 units to the right, and then he's going to go all these units to the left, and then he's going to end up with 10 units to the right. So how far is the particle from the starting point after 10 seconds? We just accumulate all these values. So he moves 10 to the right, 22.5 to the left, another 30 to the left, another 7.5 to the left, and then 10 to the right. Okay, so if I do the math for us here, this ends up being negative 40. So that indicates he's going to end up 40 centimeters left of starting point. Okay, how far is the particle from its position at t equals 2 after 8 seconds? So that means we just want to treat his starting point at 2. and figure out what his displacement is from this point forward. So we can just accumulate these values. So negative 22.5 minus 30 minus 7.5 equals negative 60. So 60 meters to the left. And then your units have to change, right? Anytime you're involving area, we know we can't keep that centimeters per second. We're always multiplying these two units together. Centimeter per second times seconds will be centimeters. Okay, so can we try these next two practices? And just keep in mind that it's all these are involving area, and then our units have to change, and what the units changes to, multiply the units of the y-axis with the units of the x-axis. Okay. All right, so try 1 and 2, and I'll work through the problem at the same time that you guys try it. So maybe you want to start off by just identifying that region between the graph and the x-axis, because that's the only region that we care about. And then we should just be able to see a combination of different shapes, triangles, rectangles, squares, semicircles, and these are all nice geometric shapes for now that we can that we don't need calculus to find the area. Eventually, we're going to have curves where area is not going to be as easily found, so we're going to need calculus to actually find the area out of the curve. Okay. Everybody okay with top of page 2? So when the graph is above the x-axis, that indicates number of people who are entering into the museum, and below the x-axis indicates people who are leaving the museum. So for number 2, the velocity graph is given to us. So the area between the graph and the x-axis will indicate the distance he's traveled, displacement, whether the distance he travels to the right or distance he travels to the left. Above means moving right, below means moving left. So I have an area of a square of 1, area of a triangle 1/2, area of a triangle below the x-axis now, so -2. And then I have a semicircle and a rectangle. I add those together, -2 pi minus 8. Another triangle below the x-axis and another triangle, above the x-axis, +1. Okay, where's the particle after 2 minutes? So 2 minutes in, he's moving to the right. So he's going to cover 1 meter and then another half a meter. Notice our units have changed, right? We started off with meters per minute, but if we're involving area, we have to multiply units together. So meters per minute times minutes will give us meters. So after 6 minutes, after 6 minutes, then it's just going to be half of the rectangle and half of the semicircle. So I can just divide that by 2. So 1 plus 0.5 minus 2 minus 4 minus pi. So we know that negative 4.5 minus pi indicates he's going to be left of where he started. So we can say 4.5 plus pi meters to the left. And then after 10 minutes, we can just add up all these values together. Okay, next up, if we can go to page 6. So all these graphs right now have been nice geometric shapes. But starting with page 6, if we're talking about area, it's going to be a little bit harder for us to find exact area when we're dealing with these graphs that are not geometric shapes. But we can do approximations of this graph between the graph and the x-axis. If we're talking about area, using area to approximate, then we want to use the easiest formula that we know, which is rectangles. So we're going to be approximating area using rectangles. We call them Riemann sums. But after that, we're going to move into finding a more accurate way to involve area. So the graph of the function g is shown to the right. Approximate the area under the curve by using left rectangular approximation methods. So we're going to create these rectangles. That's going to where the left endpoint is going to determine the height of each rectangle. Okay. So for right now, we see our graph here. And what we're going to do is we're looking at the region between 2 and 6. So I'm just going to shade in that region between 2 and 6. Okay. And it says left-handed rectangle. So what we're going to do is we want the number of rectangles based off of this formula. So the formula is going to be b minus a divided by n. And your a and b are going to be your endpoints. And then your n is going to be the number of rectangles. So here, we want to use, in this case, 4 rectangles. So your n is going to be 4. So our width is going to be 6 minus 2 divided by 4. And 4 over 4 is equal to 1. So we want a rectangle that is a width of 1. And each rectangle, we're going to use the upper left corner to determine the height. So the first rectangle, the height is at 2. So that'll be the height of my first rectangle. The height of my second rectangle, notice at 3, it's going to touch the curve at 2.5. So that'll be the height of my second rectangle. My third rectangle, I'm going to start at 4, go all the way to where the graph touches 4. That'll be the height of my third rectangle. And then my fourth rectangle, go all the way to where the graph touches 5, and that'll be the height of my last rectangle. So we know that this is not the exact area under the curve, right? There's all these gaps that are unaccounted for, but we know it's an approximation, and we're asked to build it using a left rectangular method. So that means the left endpoint is going to be the height of each rectangle. Okay, so we're just going to find the areas of these rectangles now. So the area, base times height, so 1 times 2. Second rectangle, 1 times my best approximation is 2.5. Third rectangle, width is 1, height is 3. And then last rectangle, width of 1 and height of 5. So we add all these rectangles together, 4.5. Okay, so this approximation method is called Riemann sums. And we're just using rectangles to approximate a curved region. That's basically all it is. Okay, so we'll do a left Riemann sum here. So all these, we'll try different methods here. So we're gonna force the upper left corner to touch the curve. Here we'll force the upper right corner to touch the curve. And then midpoint rectangle is where we're forcing the midpoint to touch the curve. The midpoint of the x values to touch the curve. So first off, we want to find the width. Width is b minus a over n. My a and b values are the interval, and then the number of intervals is n. So here my n is 3. So 8 minus 2 divided by 3. So the width is 2. So starting at 2, we're going to build rectangles that have a width of 2. So from 2 to 4, that'll be my first rectangle. From 4 to 6, my second rectangle. And then from 6 to 8, my third rectangle. So starting at 2, we want the left endpoint to touch the curve. So I'm going to go all the way up till I hit the curve at 6. That's where the graph touches, and I'm going to extend that height for the duration of my interval. And then that will be the area of my first rectangle. And we're doing left Riemann sums here. So that means within each subinterval, we're looking at the left endpoint and we're moving it to see to when it touches the curve. So from our next endpoint over is 4. So from 4, you're going to go all the way to the curve. Once you find that height, you're going to extend 2 units over. Now, some of these rectangles are going to sit above, some will sit below, but we don't have to worry about under or over approximation. We're just creating rectangles based off of the method. Third rectangle, left interval, left endpoint. The last rectangle is has a left endpoint of 6. So look to see where 6 touches the curve. That'll be the height of the last rectangle. Extend the graph over. And then now we have 3 rectangles. This may either over or under approximate the actual area. That doesn't matter. We're just using the approximation method that they're asking us to. So now we can just add up the areas of these rectangles. So my first rectangle has a width of 2, height of 6. So 2 times 6. Second rectangle, width of 2, height of 8. Last rectangle, width of 2, height of 6. So we're just doing width times height for all the rectangles. Next up, right Riemann sum. So same width, same a and b value, same interval, same width. So 2 to 4 is my first rectangle. 4 to 6 is my second. 6 to 8 is my third. So now we're going to use the right endpoint to see where the right endpoint is hitting the curve. Wherever the right endpoint hits the curve, it's going to determine the height of your rectangle. So I want the height at 4 to determine the height of my first rectangle. I want the height at 6 to determine the height of my second rectangle. And then I want the height of 8 to determine the height of my third rectangle. What's the height? What's the y value at 8? 0. So that means the width, the height is 0. So that means for the third rectangle, there is no area. It's just going to be 0. So first rectangle here, 2 times 5. Sorry, 8. Misread it, 8. Second rectangle, 2 times 6. And then plus 0. 16 plus 12, 28. Okay, midpoints. Midpoint Riemann sums is same interval here. So from 2 to 4, 4 to 6, and 6 to 8. But now, rather than using 2 or 4 as the determination of the height, we want to use the midpoint to figure out the height of the rectangle. So here, what's the midpoint between 2 and 4? 3. So you're going to find the height of 3 where the graph touches where the graph is at 3, and then let that represent the height of the full interval. Okay, so wherever the graph touches at the midpoint is the height of your rectangle. So here, between 4 and 6, I want to use x equals what? 5. So then look to see where 5 touches the curve, where the graph is at 5, and let that represent the height of your second rectangle. And then between 6 and 8, we're going to use 7. Wherever the graph touches at 7 is going to be highlight that point and then extend on both sides to represent the height of that last rectangle. And so now we're just adding up the areas of these 3 rectangles. Okay. Width is 2, height is 7.5 for my first. Width is 2, height of 7.5, and then width of 2, height of 3. Okay, last one, trapezoid. So trapezoid from 2 to 8, again, from 2 to 4, 4 to 6, 6 to 8. Now, the way you draw trapezoids is for each endpoint, you're going to highlight that point on the graph. So 2, we want to 2 and 4 and 6 and 8. So every endpoint interval is going to hit the curve, and then you're going to extend the graph down. And the trapezoid are going to be from point to point. So you can draw a point here, extend with a line. And so we have 2 trapezoids. Technically, the third shape is a triangle, but a trapezoid formula will also find that area as well. So trapezoids are going to do the best job of approximating. So if you look at rectangles, rectangles are going to have the way it's shaped, it's always going to create more gaps. But trapezoids, even with 3, you can already see it's minimal gap between the graph and the x-axis. So trapezoid is usually going to be the best approximation. So the formula for trapezoid is 1/2 width, height 1 plus height 2. So for my first trapezoid, the width is 2. My height is my height of my left endpoint is 6. The height of my right endpoint is 8. So 1/2 2 times 6 plus 8. Second trapezoid, 1/2 times 2, 8 plus 6. And last trapezoid, or it's a triangle, but it's going to work even with the trapezoid formula. So 1/2 times 2, and then 6 plus 0. And that's going to end up giving us an area of 34. Okay, page 7. This is going to be the most common way that AP exam is going to ask about Riemann sums. They're going to give you a table of values, and they're going to ask you the width and height of these rectangles based off of these order pairs. So we're given the rate at which water is being pumped into the tank, given by a continuous and increasing function R of t. But R of t is in gallons per minute. So anytime we're involving area, we know our units have to change. So if I multiply these two units, what's my new unit going to be?
Yeah.
Gallons. So we know that whatever we find, it's always going to be in terms of gallons, okay? Because we're multiplying gallons per minute times minute. And anytime we're doing Riemann sums, it's always area, and area always involves changing the units, multiplying your units together. Okay. So these are just some order pairs here. We don't know what's happening between the graph, but we do know that all these points are connected, and it's a smooth curve all the way through. Oh, and it says that it's a continuous and increasing. So the rate at which water is being pumped into the tank, the rate starts off at 7 gallons per minute, then 13, then 18, then 23, and 27. So the rate keeps accumulating. So we know that more and more water is being pumped into that tank. It says use the following Riemann sums to estimate the number of gallons of water pumped into the tank during the 12-minute period. So it says write Riemann sum with 4 subintervals. So 4 subintervals, that means we want to extend all the way from 0 to 12 with 4 intervals. Now, the way you draw intervals, you're going to go from point to point. So don't start at the ends, start at the middle of each order pair. So if we count, this is 1. So from 0 to 3, it's going to be 1 interval. From 3 to 6, it's going to be a second interval. 6 to 9 is the third interval. And last interval is from 9 to 12. If I subtract the x values, the t values, the minutes, that will give me the width. And the height is depending if I want a left or a right Riemann sum. So here it's a right Riemann sum with 4 subintervals. So subtract to get the width. So I'm going to put the widths up here. So 3 minus 0 is 3. 6 minus 3 is 3. 3. So these are all equal widths, all widths of 3. So we'll just do width times height. So 3 is the width of my first rectangle. What's the height of my first rectangle? 13, yeah. So this will be the left height. This is the right height. There's a height on the right, so we use 13. Second rectangle has a width of 3 and a height of what? Yeah. Third rectangle, width of 3, height of 23. And then width of 3, height of 27. Okay, is the approximation greater or less than a true value? So if we can just do a rough sketch of the graph, we know our graph is increasing. So I'm just going to do an increasing graph. But if I draw rectangles where I'm forcing the right endpoint to represent the height of each rectangle, what do you notice about all these rectangles? They're all gonna sit above the curve, right? So the area of these rectangles will be higher than the actual area. So we can just say over approximation, because right Riemann sum on an increasing function. Let me do a midpoint with you. So midpoint Riemann sum with 2 subintervals. So 2 subintervals. So now we want to go from 0 to 6. And then second interval is from 6 to 12. Okay. What's the width of my first rectangle here? 6. Second rectangle, also 6. And then the height, you're going to choose the middle height. It's not necessarily, you're not going to do the average of these numbers. You're just going to pick out whatever is in the middle. This doesn't have to be 3. It could be at 5. It could be at 1. The middle doesn't mean exactly middle. Middle just means in between. So the height in between is going to be 13. And the height that's going to be in between is going to be 23. So width of 6, height of 13. Width of 6, height of 23. So midpoint Riemann sum is going to be 6 times 13. Okay, your homework is just to finish up page 7. I'll send out a reminder this afternoon. Yeah, we have an extended advisement, so because of the readiness check, you know.
I did like 75%. Like the first time, they had everyone looking at the talking scene. Because I did. I did 8. Well, I was just trying to see what I. Yeah.
No, it's actually.
Wait, I should be able to give it back to you later this week.
Yeah, you guys are just anyway. I got 20 minutes.
See you in a good.
Paste it on. I like go to every single question. Oh yeah, I forgot. It doesn't just like show. And it's they're actually easy.